All right, great. I have started recording. Let's start chatting. Speaking of chat, I have the chat window open, so you're welcome to interrupt me for questions or just post them in chat, and I'll notice them at some point, I promise, and then get to your questions then. So by the end of today, I'm hoping that we'll kind of have every bit of knowledge that we need to talk about actual MRI sequences. Maybe we won't get that far, but I think we probably will. I'm optimistic. I'm going to start by kind of touching up a couple concepts that I covered last time, just to add a little bit more detail, give you guys some interesting context that I forgot to mention last time. And then I know that last session we kind of ended saying gradients are the next step, but I have done some shuffling around. We're going to kind of dig a bit deeper into T1 and T2 mechanics to kind of understand what's going on with those two curves that I drew last session. And then we'll get into gradients and go through some of their different applications for spatial encoding in MRI. And that's kind of where I'm expecting we'll end today. If we have a little bit of time, we'll actually jump into what a pulse sequence diagram looks like, which is kind of just like a drawing of what an MRI machine is actually doing when we're recording signal, when we're actually taking an image. All right, so the first thing that I wanted to kind of just chat about is the B0 field. This is the main magnetic field that the MRI machine is outputting all the time. If you've done any safety training with MRI, you know that the magnet is always on. That's because this B0 field is always present. And I just wanted to give you guys a bit more context if you don't already know. The B0 field is high strength, so 3 Tesla is common for the, it's kind of maybe like the research standard these days for an MRI machine. Clinical machines, you might see 1.5 Tesla. Also, that was like a previous standard. It's also still quite common. And then there's, high field MRI, stronger magnets where 7T or 11T are possible. But at the 3T level, that is a very strong magnetic field. And to give you guys an idea of how strong, contextualize it a little bit, that's roughly 60,000 times stronger than the Earth's magnetic field, the thing that you would use to navigate by compass. It's kind of a number that's so large that it's not really relevant, but maybe it'll help you kind of understand this is a very strong magnetic field. And another thing I just wanted to kind of mention here is that this requires some pretty fancy electronics to achieve, because you would think to generate such a strong magnetic field, you would need a lot of power or a lot of current running through this coil of wire, and that's kind of the orange lines that I've drawn. This is my beautiful MRI drawing, and the orange lines are showing that in this, the circle of the MRI machine, kind of like wrapped around the bore, is a huge amount of wire. If I remember right, it's copper, but I could be wrong. It's conductive wire. There's lots of current that's running through it, and that's what's generating the magnetic field. Now, current running through a wire generates heat. There's some resistance there unless the wire is superconductive, and that's actually required for MRI. So I'm just going to make another note here. This is achieved. Make it orange so that we know this is actually referring to my beautiful orange lines. So it's achieved with superconductive coils. And if you don't know what a superconductor is, this is any material that when it reaches certain conditions becomes a superconductor, which means that there's zero resistance in the material anymore. And that means that current running through, including a very large amount of current, can pass through the coil with no resistance, and it can actually stay in the wire indefinitely without a power source. So if you reach these conditions, you can put in a lot of power and the current will continue flowing through the wires, continue generating that magnetic field. You don't actually need to keep powering the machine to keep that field going. What you do need to do, though, is keep the wires very, very cold. That's what allows them to become superconductive. So I'm just going to make another note here. In MRI, they're cooled with liquid helium, cooled by liquid helium. Some of you may already know, but generally the temperature of liquid helium is about 4 Kelvin, so just a few degrees above absolute zero. Very, very cold, well, almost as cold as space on average. So that's why you need liquid helium or just helium in general to run an MRI machine typically, because the wires here need to be kept very cold in order to become superconductive and generate that strong magnetic field. So that's kind of just I don't know, an extra note that I think is really cool about MRI machines and is worth kind of appreciating, that these machines are very, very fancy, essentially. All right. The next thing I want to talk about, again, just more context for what I talked about last time. We talked about how the net magnetization vector, I've already forgotten that, that acronym. It's generated when you have hydrogen atoms or protons or spins. All three of those terms mean the same thing in this context. When you put them in a magnetic field like we just talked about, they will align either parallel or anti-parallel to the field. Sorry, I need a red marker here. So hydrogen atoms or protons that I'm representing here with these red dots or red circles that have a magnetic field with an orientation. That's what the arrow is representing. In a magnetic field, they align either up or down with the B0 vector that I've drawn there. That's the main magnetic field. And we know that this parallel orientation is a lower energy state. Lower energy state than anti-parallel or than down. I'll just draw that out here. So there's a slight surplus of hydrogen atoms that align upwards, producing this net magnetization vector that has an orientation with the main magnetic field. And what I didn't mention, so I'll just make that note here. So I guess it's kind of the same as above, but there's more up than down. Because of the above note. Now, yeah, what I did mention, I just wanted to run past you guys, is in the body. So in the body, there's about, there are 10 to the 25 hydrogen atoms just kind of bouncing around. There's quite a few of these guys. Keep it red so that we know that's kind of associated with the above diagrams. And from this population, about 1 in 10 million, oh, that 6 is kind of unclear, about 1 in 10 million of these protons, about 1 in 10 million of these protons is oriented in the up direction above and beyond the balance of up and down. Did that make sense? So if you consider a population of 10 million protons in an MRI scanner, there will be approximately 49,999,999 down orientations and 50,000,001 up orientations for the spins. So there's one extra in that 10 million population, I guess. Just kind of give you guys an idea of how this surplus of up orientation spins or protons is fairly small in ratio, but because we have so many protons in our body, it produces a significant NMV or net magnetization vector that we can measure and mess around with. I should actually finish my thought here. 1 in 10 million extra up orientation. Hopefully that makes sense. Just a little side note that might help things make a little bit more sense. And the last thing that I want to touch on that we went over last time is I kept drawing the B0, or sorry, the B1 field, the extra magnetic field that we apply to our NMB to tip it. I kept drawing it as a sine wave, like I've got in the little title thing up there, just up and down. But I didn't draw the B0 field in that way, right? So in case anyone's confused about why, I kind of talked about this last time, but I just wanted a couple of diagrams to make sense of why this is represented as a sine wave. It's because of the requirement for magnetic resonance. When we're tipping the NMV, we have to apply the B1 field at the resonant frequency of the NMV which we know from last time is the Larmor frequency, or the precession rate of the individual spins. Kind of a quick review. Hopefully this is all ringing a bell for you guys. If not, just interrupt me or put a question, and then we can talk about that in more detail. But in order to actually tip the NMV effectively, we need the B1 field to precess at the same rate that our NMV precesses. So just kind of a couple diagrams here. We've got an NMV that I've drawn here that is tipping. So we've got our, where it started is a dotted line, and now it's tipped some direction from the z-axis towards the x-axis. The B1 field is aligned with the y-axis because you need a right angle between the NMV and the B1 field to actually get this tip to happen, thanks to the right-hand rule. And if we consider this B1 field from a point of reference, which is a transmit-receive coil, which I talked about last time, it's just a coil of wire that we can use to record signal or actually generate this B1 field. It's an orange box that's kind of aligned with the y-axis coming out of the page in this example. If you recorded the signal from the B1 field from that point of reference in this time 1 example, and the y-axis on this little black line is amplitude, go away, then the signal will be somewhere up here. Just want to get these controls up the way that have popped up on my screen and go back to black. Great. So this is amplitude. And if I just draw the same thing at 2 different time points. Sorry, I've got the viewing controls of Zoom that are blocking my choice of markers, which is troubling. But so time 2, the B1 field has kind of precessed. I should draw some arrows. It's meaning to. Blue. Okay, so as the net magnetization vector is precessing around the z-axis, as it's wont to do, the B1 field is also going to be precessing at the same rate, that resonance condition. I see a question. I'm just going to finish this up and then I'll read that question. So time point 2, same thing. I'm just going to only draw the B1 field for brevity's sake. And time point 3, we've got this B1 field that's rotating in a clockwise fashion, I suppose, around the XY plane, right? So if I draw those, I would really love to get rid of these. Okay, well, that's fine. That works. Now those controls are in the way on the bottom. We'll see if that backfires. At time point 2, our measured signal from that point of reference, it's going to be actually near 0, as the B1 field is kind of oriented perpendicular to the point of reference. And at time point 3, it's actually going to become strongly negative. The same kind of amplitude as it was strongly positive before. So if I just label these time points, time point 1, 2, and 3 on this diagram, and then hopefully this is kind of coming together for you guys. But if we draw a line that's fitting these 3 points that I've just drawn here, it's going to look like a sine wave. And I'm just going to keep drawing it through some other imaginary points 4 and 5, where the B1 field continues to precess. So I'm drawing the B1 field as a sine wave because if you measure from a point of reference, then that field is going to be varying because it's rotating with the NMB to cause that tipping to happen. So hopefully that makes sense. Maybe you guys already knew that already, but I just wanted to make it really clear because it's something I kind of glossed over a little bit. Okay, so we've got a question. What determines the fraction of protons aligned with B0? There are more protons aligned when it's a stronger magnetic field, like if you use 6 Tesla instead of 3. Yeah, thanks for the question, Catherine. That is right. So I briefly chatted about this last time, but like I mentioned, the parallel alignment of protons is a lower energy state than the anti-parallel alignment, and this actually varies with magnetic field. I think it's called the Zeeman interaction. It's in the book. I was just going to flip to the page, but I'll just move along. The actual name isn't really as important as the concept. But it turns out that if you increase the magnetic field, the difference in energy between parallel and anti-parallel increases, which means that there's going to be a bias towards even more protons in that surplus of up orientation, producing a stronger net magnetization vector for us to work with. So that's one way for us to increase our kind of like signal to noise ratio, which will come up later. It gives us more signal to work with, and that lets us have higher resolution images and all these great things. There are other factors that are going to be influencing your NMV magnitude, but they are a little bit more detailed than the level I'm talking about MRI right now. But one thing I'm just going to run by you is the type of tissue that you're in is also affects how many extra protons are in the up orientation. So when you're considering a net magnetization vector, it's actually contributed. There are different amounts of magnetization contributing to that vector from different tissues. For example, you get less signal. Well, I actually don't know if that's right, so I will just not be specific right now, and maybe look that up for next time. But yeah, the type of tissue that you're in affects how much magnetization there is from that tissue. There's even more than that, but that's just one that comes to mind. All right, so we're just gonna move on. Happy to answer any follow-up questions there if anyone has any. But yeah, the main factor in the NMV magnitude is field strength for sure. So stronger magnets, more signal to work with. Okay, so now we're gonna go back to talking about T1 and T2, which I kind of briefly ran through last time and then realized I glossed over a lot of important stuff. So we're gonna jump into it in a bit more detail here. All right, so just kind of briefly refreshing what I talked about at the end of last session. When we are tipping our net magnetization vector, I've just got a couple like stages here to help us visualize what I'm talking about. During excitation, when the B1 field is being applied along this axis in the transverse plane over here, we have our net magnetization vector that started. Is that right? Yes. It started up here, and then I'm just drawing it at some arbitrary point as it's tipping downwards. All of our kind of toy examples are considering like a 90-degree pulse, and so we want this net magnetization vector to kind of align with the B1 field at the end. So if I draw that in the post-excitation stage, then our NMV started up here at about the same amplitude as I had in the last diagram, but now after excitation has ended, it's fully in the transverse plane. There's been a 90-degree tip from its original orientation to its current orientation. So I'll just draw that with kind of like a little 90-degree symbol, and the B1 field is gone at this point, right? It's done its job. We've turned off that extra magnetic field, and now the NMV is free to do what it wants to do. What it wants to do is return to equilibrium, just return to that upwards orientation, and also precess, like spin around like crazy, just because of the interaction between the net magnetization vector's current alignment and the B0 field. So it's kind of pulling it back upwards. So immediately post-excitation, when the B1 field is gone, our NMV is at the 90-degree. I guess it's been flipped 90 degrees in this example. And then in relaxation, which is kind of like the NMV returning to its equilibrium state, we have the reference state where the NMV was in the transverse plane, and now it's actually tipping back upwards, right? It's going back to that 90 degree, or to that B0 orientation, that alignment with the B0 field. So this is what I kind of chatted about last session, and it's easiest to explain things this way as once you kind of dig into what's going on with individual protons, like we were talking about at the very start of this workshop series or set of sessions. Things get a lot more complicated and quantum and messy. So typically it's convenient in MRI to talk about what's going on in terms of like classic vector physics and just kind of classical physics and the interactions between magnetic fields that way. But sometimes it's useful to break it down and ask what's going on with individual protons. So I want to kind of talk about that above and beyond the NMV based understanding we have right now. So, and somebody asked about this after last session, so thanks for that question. This is why we're going over it in a little more detail, because it is it's a very good question. Okay, so with these 3 time points that I've drawn above, I'm going to tell you kind of what's going on with protons at each point. But first, I want to kind of give a visual of the longitudinal component and transverse component of the NMV, because I'm drawing kind of like the vector itself. But for this next little, for the next while of the session, actually, we're going to be kind of breaking it down into the longitudinal component, which is aligned with the B0 at all points, the Z component of the vector, and then the transverse component, which is in the transverse plane, orthogonal or 90-degree or perpendicular, I guess, to the longitudinal component. So I'm going to go back to this very nice example from the MIOS website and just play it a couple times so that we can get an idea. So in this case, the red arrow here is representing our longitudinal component of the NMV. The yellow is our transverse component. You can see how they never change orientations. They're always aligned with their respective planes. And then the orange arrow here is our NMV itself. And you can see it's precessing and it's regrowing and going back to alignment with B0. So in this next little bit, we're going to be talking about the red arrow on this animation specifically. You can see that after excitation, which is going to start again right away, the arrow is getting smaller, it becomes 0, and then it regrows. It goes back up to its original magnitude, right? So that's the kind of like longitudinal excitation and regrowth trajectory, I suppose. So in that context, during time 1, we've got this surplus of protons that are aligned parallel, bringing about our NMV. And during time 1, during excitation, we have these protons that are aligned upwards. They are actually absorbing energy from our B1 magnetic field. And that is because they've absorbed energy, they're entering a higher energy state. That is the downwards orientation, right? So we have protons that are actually flipping orientations, moving from the parallel state into the anti-parallel state. And if we just think about kind of the sum of magnetic fields that's creating this NMV, if we have some of the up orientation protons flipping to down, that's going to decrease our longitudinal component of our NMV. Does that make sense? So our longitudinal component is actually getting smaller during excitation, as you might expect, because protons are actually flipping and they're absorbing energy from the applied magnetic field and flipping into an anti-parallel state. Now, with a 90-degree pulse, we're actually going to be applying this B1 field until the number of up orientation or parallel orientation protons is equal to the number of anti-parallel orientation protons. So this is what's actually happening at the proton level when we have our 90-degree pulse. There's no longitudinal component to our NMV, and that's because at the actual proton level, there's a balance between our up orientation and down orientation of spins. And then during relaxation, what's happening is these sum of the downward orientation protons, they once there's no incentive for them to stay in their downward state, they want to return to their lower energy state, right? If there's no driving force that's actually pulling those protons into the antiparallel state, they'll just kind of throw their energy away and return to the lower energy state, to that equilibrium. So in this case, or the way that I'm describing it anyway, some of these downward oriented protons will release their energy and return to the parallel state, right? So I'm just going to write down release here, maybe energy. See if I can fit that in. Sure. So in order for this to happen, a proton needs to find a willing receiver of this energy. And this happens, sorry, I'm getting some Slack messages. Maybe I'll mute it at the break. So in order for the downward oriented protons to return to the parallel state, they need to get rid of their energy, and they do that through interacting with nearby molecules. this is happening through a process known as spin lattice relaxation. So I'll write that down here. And so step 3 occurs. Let's switch to purple here once I spell through correctly. Through spin. Oh, that is thick. Spin lattice relaxation. And what that means, the lattice word there is referring to surrounding materials that are not protons. So anything that is around that is not a 1H proton. And effectively, this means that the energy is getting removed from our net magnetization vector. It's just kind of going into the ether, into surrounding tissue, and it's not contributing to our measured signal in MRI anymore. So the reason the T1 times are different, I had kind of a small table at the end of last session showing that water has a long T1 time. It takes quite a while for this process to happen, whereas gray matter and white matter have shorter T1 times. The reason for that is because there's kind of just more different tissue in gray matter and white matter than in water or CSF. CSF, as you can imagine, is fairly homogeneous. Sorry, I talk about the brain because I'm a brain researcher, but if any of you are body, other body parts people, the same concepts apply. Just kind of like more, less watery and more tissuey, more human tissuey tissue. Oh boy, I'm floundering here. Anyway, tissue that has more complex materials allows for more chances for protons to kind of pass their energy off to something else. Water itself is fairly homogeneous, so there's not really much chance for a hydrogen atom to give their energy away to something that isn't another hydrogen atom, just because there's a lot of hydrogen in water. So that's why T1 times vary between tissues, and this will come up again and again as we talk about T1 weighted images and all this fun stuff. But for now, we can kind of summarize this. Maybe I'll write that during the notes, just so we don't kind of slow down too much. But just summarizing, we have our tipping of our net magnetization vector with a 90-degree tip. There's no longitudinal component until the B1 field is turned off, and then the NMV is allowed to kind of regrow in that direction. It's not being pulled into the transverse plane anymore. At the proton level, protons in the parallel state are absorbing energy. They're entering that higher energy state of anti-parallel. With a 90-degree flip, the number of up and down protons is equal, resulting in no net magnetization in the Z direction in the B0 field orientation. And then during relaxation, the protons that are in the higher energy state are looking to kind of offload their energy and become lower energy protons again. They want to kind of follow the path of least resistance. Yeah, I've got another question from Catherine, which is great. Do protons only have the 2 energy states, like a binary either up or down, or are there in-between angles of the NMV? I think, so this is an area where I'm still a little bit confused, but it's just because it depends on the level of detail you want to understand MRI at. For our purposes, there are 2 orientations, either up or down, and that is true. It's just kind of due to the interaction between a hydrogen atom and the main magnetic field. There are 2 energy states that hydrogen protons or atoms can possibly have, either aligned with or against the main magnetic field. And that's essentially what this book is telling us, so I believe it. But when I talk to some people about kind of why this is the case, when I was preparing for my defense, I got some kind of nuggets of wisdom that, at the actual quantum level, which again is beyond the scope of this course, but when you consider quantum mechanics, there's more of a continuous distribution of hydrogen atoms. It's just that they kind of return to these up or down states, so they're kind of biased towards being in these states. And there's hydrogen atoms doing all kinds of crazy stuff in the body all the time, is really the main takeaway. But at least when you actually simplify down to what happens and what matters for MRI, the up and down states are what's actually contributing to our NMV, and we can kind of ignore the rest of the quantum mess that's happening all the time in our bodies. So hopefully that was at least a little bit useful. But yeah, in this kind of like, at the level of knowledge that I am teaching, there are up and down states, and that's how hydrogens are aligned with the main magnetic field constantly. All right, cool. So let's move on back to that graph that I drew last time. Let me get rid of some space here in my notes so we have the title on the graph on the same page. Cool. All right, so I already drew this once, but the actual curve that we observe when we're looking at the longitudinal component of our NMV is an exponential growth curve. So it looks something like this. See how good my drawing skills are today. Decent, I would say. Okay, and then, so this is kind of like, I should put a label on here. Let's kind of make it semi-accurate. So if this is kind of at the maximum magnitude of our NMV, its equilibrium state. It'll take some amount of time, which is the bottom axis of this graph. And could be better. So time in milliseconds. I actually want to move that label over, give myself more space. Okay, so it takes some amount of time for the NMV to return to its equilibrium state, and we can quantify this curve through the useful constant of T1, which we heard about last time. I'm going to say it's roughly around here. It's probably a bit too high, but it's fine. So there's this T1 constant that I just mentioned is different between tissues. That is the amount of time that it takes for this curve to return to 63% of its maximum amount. This is useful as it, well, it helps us kind of get good images and is different between tissues and has all these nice properties. So someone at some point decided that T1 was the way to quantify this curve, and they made a pretty good choice. Now I mentioned that T1 for tissues can be somewhere between like maybe 2,000 to 4,000 milliseconds. And because this is an exponential growth curve, we actually have kind of like decreasing amounts of increase over time. So at the time constant of 2T1, like 2 times the T1 time, I said time a couple times there. Oh no, it's happening again. So just kind of drawing this again. At 2 times T1, the amount of magnetization that has kind of been recovered is 86%. So it's much less than during that first T1 period. And then if we go all the way out to three T1 durations, this is our last one. That number is up at 95%. My dexterity today is lacking. It's fine. I'm just going to move this 100. Oh no, made a huge mistake. Oh, I don't even have an undo button, so I'm going to have to manually draw this. I'm so ashamed. Okay, so at 3 times T1, that amount of magnetization that's regrown in the longitudinal direction is 95%. Hopefully this is making enough sense. And if we kind of appreciate how long that is, that's, you know, even if our T1 in gray matter is like 2,000 milliseconds or so, 2 seconds, that means after 6 seconds of letting the brain kind of recover after the B1 field has been turned off, the full amount of magnetization still hasn't even, like we haven't even achieved that in our NMV yet. So it can take quite a while to allow our NMV to regrow. This causes some time constraints on MRI, and we'll kind of get into how we work around those as best as possible later on when we talk about kind of steady state mechanics. That's probably for next session, I would say. But just to kind of write a note here, so if T1 in water, as I said last time, is around 4 seconds, then our NMV hasn't fully recovered after 12 seconds, which is a long time. Water is a slow tissue, and that is the main takeaway, I would say, of this whole series is, come on, water, you're so useful, but also so slow. So sometimes we need to wait quite a while before we mess with the NMB again to make sure we get enough signal. There's more to it than that, but we can just kind of leave it there for now. So hopefully this gives you kind of a better appreciation of what's going on with this T1 curve. It can take quite a while for longitudinal magnetization to regrow, as I just kind of mentioned here. We've got that exponential growth pattern as well. Okay, happy to stop for questions, but otherwise we're going to move into the transverse component of our NMB. And after this, we'll probably have a break. Then we'll dive into gradients and then we'll be done. It'll be great. Okay, so refreshing us on what's going on with the transverse component. It's got all this precession going on, which is great. We're looking at the yellow arrow now. And over time, it's actually decreasing or decaying. Getting smaller as the NMB in orange returns to that longitudinal orientation. The transverse component disappears. And I mentioned before, this happens much more quickly than any change in the longitudinal component, which you might be able to appreciate here. It takes quite a while for the red vector to become large, whereas it happens quite quickly that the yellow vector there becomes smaller. It gets smaller much more quickly. Kind of talking in simple terms, but hopefully it's useful. Now I'm just going to make one more note on this animation that, again, with that kind of point of reference that's recording a precessing magnetic field, that's the signal that we're getting on the left there. That's called free induction decay, and we'll touch on that after our transverse magnetization at the end. But this is kind of helping us visualize why our signal that we get is a sine curve. It's because the yellow vector here is spinning around, which is kind of varying the amplitude of the signal that we record at any point. Okay, so getting into what's actually happening with the transverse magnetization, let's do that. Just gonna pull up my next figures. Okay, so for this portion, I'm going to be talking or drawing diagrams that are kind of looking from the top down. So our X and Y planes are to the left and right, and the Z axis now is kind of coming out of the screen. So I guess that way for you guys if you're looking at my camera. Z axis is coming towards you. I got a question about why spin relaxation is so much shorter. I will definitely get to that. It'll just take me a little bit. I'm going to kind of start at the basics and build up to that. So at equilibrium, when our NMV is oriented with the z-axis, kind of oriented out of the page here, I'm just going to write down a heading here. Oh no, equilibrium. Okay, I'm going to draw 6 protons. Now I'm just going to draw them as dots because we're looking down at the top of them, and I really only care about the transverse component of their magnetic fields. As we kind of mentioned during last session, the orientation of these magnetic fields is kind of continuous and randomly distributed, so they can be doing whatever it is that they want, but all of them are going to be precessing in the same direction, it turns out. So I'm going to draw just some clockwise arrows to kind of get at that. So we just got all these different spins. They're all precessing in the same direction, but they're oriented however they like, which means that our transverse component of the NMB is 0, right? Which I'll just write down. Hopefully referring to transverse magnetization makes sense to you guys. It's just the component that's in the plane that's 90 degrees or orthogonal to the Z plane. Sometimes called the XY plane instead. Transverse is shorter though, or easier to say. Now, if we look at the post-excitation state, like I had up above, where again, we're using a 90-degree kind of toy example, where we have a 90-degree flip. When we look at these spins again, what has changed is that there has been an external magnetic field, a B1, that has actually synchronized the precession of these guys. Hello. Okay, great. My marker disappeared for a bit there. So now, all of these spins that were previously at any phase of their precession cycle that they wanted, they're now all spinning at the same rate, thanks to the Larmor frequency equation that we talked about. And they're all spinning in the same direction, thanks to the right-hand rule. And what this means is that we have a net magnetization vector component in the transverse plane, right? So I'll just write that down. In the post-excitation state, we have a net magnetization vector. Just forgot how to spell net magnetization. And that's in the transverse plane. And as I'm sure you guys can imagine, it makes sense for this vector to be oriented in the same direction as those little magnetic fields, right? Because they're all summing together to become one transverse component. That's the yellow vector that I had up on that previous animation. So that is essentially what's causing transverse magnetization to grow. When we consider our NMV components, it's actually synchronization of the precessional phase of different hydrogen atoms. So at the level that we're talking about, these hydrogen atoms are still in their up and down orientations. They're not actually becoming aligned with the B1 field like you might expect. They're actually staying in the up and down orientations like we just talked about, but the phase of their precession is now synchronized. So all of their transverse components are kind of adding up to one big component, right? So I'm just gonna kind of write that down here. So application of the B1 field causes proton precession to synchronize. And if that doesn't make sense to you, please let me know so we can kind of get on the same page here, or I can explain it a different way maybe, just because it's pretty important for the rest of the stuff that we're talking about. Actually, just like understanding that our spins remain oriented up or down, but the transverse component is because they're all precessing it at the same phase now. They've all become synchronized in phase. I'm saying the word phase a lot because that's an important concept, and if it doesn't make sense, then we'll need it to make sense. Otherwise, a lot of things won't make sense. All right, if that wasn't confusing enough for you, let's talk about when protons don't all precess at the same rate. So previously, I established the Larmor equation for you guys, which I'll just write again, although I would like it to be thicker than that. The Larmor equation. And that was that our precessional frequency, which I just have as a fancy F, is equal to the gyromagnetic ratio of whatever particle you're caring about. For us, it's hydrogen protons. And that's multiplied by the strength of the magnetic field that the particle is in. So I'm just going to write down precessional frequency here. All right, so we know this, right? Now, there's a bit more nuance to it than that. The actual, in reality, not every hydrogen atom is going to be precessing at exactly that rate. And that's because not every hydrogen atom is experiencing the exact same magnetic field for a variety of reasons, as we'll get into. But the most, like the consistent, irreversible, intrinsic reason that protons are experiencing different magnetic fields is because they influence each other. So precession frequencies, and this is the main principle of this slide that I'm drawing here. Precession frequencies are influenced by interactions with other nearby protons. So what this means in diagram form is just consider two molecules of water, right? You've got two oxygen molecules, we've got some covalent bonds to two hydrogen atoms. The oxygens can do what they want. We're not interacting with them in MRI typically, or maybe at all. I've never heard of oxygen imaging. But these hydrogen atoms we care about. And we've been talking about how they can be oriented up or down, and how down is a higher energy state. So one thing I did mention during spin lattice relaxation is, in order for a hydrogen atom to give its energy away, it needs to find a particle that's similar to it, that's kind of vibrating at a similar frequency, that is kind of like nearby enough that they can interact. And when you consider these two water molecules, these 4 hydrogen atoms, they're all precessing at a very similar frequency, right? Thanks to the Larmor equation, they have very similar properties because they are the exact same type of atom. So that means it's actually quite easy for this hydrogen atom that is in the down orientation to exchange energy and kind of give its own energy away to this nearby hydrogen atom, right? And so I'm going to kind of change the state of this diagram and say now that there's been an exchange of energy, this hydrogen atom has become an up orientation and this one has become down. There's been an exchange of energy, right? And then the exact same thing can happen again. That energy can be passed to this hydrogen atom and it can bounce back and forth. And maybe it skips one and goes over there. But anyway, there's molecules that are nearby that can exchange this energy that's been added to the system thanks to the B1 field. And this change in energy, this fluctuation in parallel and anti-parallel orientations, it causes fluctuations in the magnetic field. Sorry, I just noticed some questions in the chat. I'm going to finish my point and then we'll go back there. So here, energy can be exchanged. And that's because these atoms have very similar conditions. Or I'm going to say similar properties here. In that diagram, and this causes small fluctuations, but still fluctuations. And those fluctuations are in the local magnetic fields, all right? So the main magnetic field doesn't change. It's just that there's extra interactions that can either like kind of add to the magnetic field or subtract to it, or subtract from it rather. Okay, so we got some questions. Right, yeah. Okay, so the question here is, I thought the B1 pulse caused the NMB to flip into the transverse orientation. It also syncs them up. Yes, essentially. This is because this kind of misalignment of ideas is because we're switching from talking about kind of classical physics and vector interactions, where, you know, if you have a vector that's exerting a force on another vector, it can cause some tipping. And that kind of view makes the most sense for MRI. When we just kind of ignore what's happening to the protons and talk about it in terms of classic vector physics, it's the simplest and it actually describes MRI physics very well. So for the most part, we talk about vectors. But it's still useful to understand what's happening at the proton level sometimes. And that's what we're kind of focusing on so far today. And in that case, where we're looking at the protons that are kind of making up that net magnetization vector, we can no longer talk about it in terms of, you know, 2 vectors interacting with each other, because now we have many small little particles that are all doing their own thing at the quantum level. So this is, you know, we're kind of dipping our toes into the quantum mechanics of MRI. But I'm not giving you kind of the full quantum picture because that gets very confusing, but this part is understandable. So when we look at what's happening with protons that are kind of making up that net magnetization vector, the reason that we have a growth of a transverse component is because their precessional frequencies synchronize. So that's essentially, there's a difference in how I'm explaining that idea. One way to think about it is, you know, the vector tips, and then the reason that vector precesses is because now there's an interaction between it and the main magnetic field, which is, you know, causing it to spin as it regrows. That's one way to talk about it. And then if we dig down into the proton level, you know, the kind of mechanisms behind it are that, you know, those protons generally stay oriented up and down, but their precessional phases synchronize. So it's 2 different ways of looking at the same thing, and they don't necessarily you know, line up when you try and combine the 2. They're just kind of 2 separate models that explain the same phenomenon. Hopefully that helps a little bit. This often trips me up as I'm trying to, you know, talk through these things as well. So I hope it's not too confusing. And I hope my explanation helped a little bit. Chelsea has a note about how bold imaging is more focused on oxygen. Yes, but so that's true. Oxygen is like a very important molecule and how fMRI works. But what I was just kind of like muttering to myself about is in fMRI, we're still working with hydrogen atoms, and the net magnetization vector is still it's still made up of hydrogen protons that are oriented up or down and precessing and all that stuff. Whereas if we were actually doing oxygen imaging, we would be working with oxygen atoms instead. This is the first time I touched on this concept, so I probably shouldn't have, just to keep things simple. But you can work with other atoms in MRI that aren't hydrogen protons. It's just generally we use hydrogen because there's a lot of it in the body and it has a large gyromagnetic ratio, which will be relevant for gradients. But there's also like sodium imaging, for example, is another common one. You can work with sodium molecules in the body, and then if you do something like that, you get completely different images of the body because the locations that there's a lot of sodium in the body might not be the same as the ones where there's lots of hydrogen. So that's kind of what I was talking about when I was talking about oxygen imaging. I don't think that happens. I don't think oxygen is a molecule with a meaningful MRI response. But we will get to fMRI, and then my rantings might make a little bit more sense. Okay, so we okay, we're about halfway through. I'm going to choose to toss our break in here. We'll come back and wrap up our transverse dephasing talk and then jump into gradients. I want to make sure we have enough time to get through that, but I also don't want to just like dump information on you and confuse you too much. So let's have a 10-minute break. I think we can still fit everything in at 11:15, just to give people enough time to kind of, you can go do your own thing, eat some food or whatever. So we'll resume our recording and our lecture at 11:15. And until then, time is yours. I'm going to stop my recording here. All right, so recording is back on. Let's continue. So we just ended chatting about how hydrogen atoms can exchange interactions with each other, causing little variations in the local magnetic field. Oh, I forgot to write the word field here. That would help. So this process is called spin-spin dephasing, not spin lattice relaxation, but spin-spin dephasing. Draw that in purple. Okay, I'm gonna write out a full sentence here. Make it bold because it matters. So, loss of transverse magnetization, the transverse component of the NMV, is driven by spin-spin dephasing. And spin here is referring to a hydrogen proton, right? So it's one proton interacting with another one. I'm just going to add a note here that might not make too much sense until later, but this process of spin-spin dephasing is irreversible. And we'll dig into that when it matters, but just to have that there, this process is intrinsic. The longer that you let the longer time that you allow the NMB to relax or return to its equilibrium, the less signal you're going to have in the transverse plane because of this dephasing. Now, a diagram that'll help us understand why this differences in precessional phase causes loss of signal in the transverse plane. That's coming up next. I'm just gonna move that title down, give myself a bit more space. Kind of combining two sections into one here just to save us a bit of time. So similar to what I was doing before with the longitudinal stuff, the T1 stuff, I'm going to draw some time points and break it down from there. Okay, so at the post-excitation state, and then over here we're just going to have, further in time. So at state 1, we've got this great net magnetization vector. I would love to undo that. I'll just draw over it. It's all in the transverse plane. Just going to note this is still the transverse plane. So this might be the y-axis, this might be the x, but then z is kind of coming out of the screen at us still. And this NMV is precessing. I'm going to keep drawing in the clockwise direction. And then if we kind of come back at the amount of time it takes for this NMV to complete one cycle, right? One phase of its revolution. There are going to be some of these spins that are contributing to the NMV that are precessing faster than the main population, and some that are precessing slower, right? So now, if we kind of come back a little bit later and allow this NMV to precess, what we have is not just one vector anymore, but I'm going to draw three smaller ones. One in green that is precessing a little bit faster than the NMV, or than the Larmor frequency, than we might expect, right? And one in purple that is precessing a little bit slower than we might expect by the Larmor frequency, right? So immediately in this second diagram, we can see that there's been a loss of coherence, right? Not everybody is at the same phase of their precession anymore. That's why this is referred to as kind of a loss of phase coherence, or as transverse dephasing or transverse decay. I said decay weird, but anyway, all of these are kind of getting at the idea that differences in precessional phase cause an irreversible loss in transverse signal. And if you remember, we record signal from MRI in the transverse plane, so this is very important. And if we come back, say, 2 more cycles, just gonna note this is kind of my idea here, just to say, hey, we're giving some time for the NMV to precess 2 more times. This is just only going to become more pronounced as within that faster population, there's probably a subpopulation that's precessing a little bit faster than other ones. So dephasing is going to occur even more, in a more pronounced fashion, because we've given more time for this process to take place. Purple ones are still slower, and green ones are still faster. And I hope that you can kind of imagine that if our point of reference, our actual recording devices, is up here, then in the first case, it's going to see, if we record immediately after the flip, it's going to see a very large net magnetization vector. And then at point 2 here, that NMV is already going to be a fair amount smaller, just because we're adding up we're adding up the components that are in this direction towards the receiver, right? If we add up just those components, we're losing some of that magnitude because these vectors have components in the lateral directions as well. And then same thing at time number 3 here, this NMV is going to be even smaller, and this happens quite quickly, right? So hopefully that makes sense and kind of helps to explain why dephasing is such a pronounced and quick process. Because essentially very soon after, well, immediately after you remove the B1 field and remove the force that's kind of causing spins to precess in synchrony, these spin-spin interactions are going to cause some protons to precess faster, some to precess slower, and this happens quite quickly. So if I may have done this last time, but if my fingers are all orientations of magnetic fields in the transverse plane, they immediately start to spread out and become very messy, as far as I can spread my fingers. But eventually they'll, be in all directions, become continuous, and that's when our transverse magnetization is gone, right? When all protons are back to spinning at whatever phase that they want, and that's due to differences in their local magnetic field conditions. So 2 questions that I can kind of address here. One is that question of why is spin-spin relaxation so much faster than spin lattice relaxation, right? Why are T2 effects so much quicker than T1 effects? Essentially, it's easier for hydrogen atoms to exchange their energy with other hydrogen atoms, for them to get rid of the energy with their, the background lattice, like I was talking about. So that essentially means that these local, very small fluctuations in the magnetic field they're present all the time, everywhere, and the physics behind MRI are never perfect to have every hydrogen atom experiencing the same magnetic field, right? So dephasing happens immediately, whereas you need to allow more time for hydrogen atoms to get rid of their energy instead of passing off to another hydrogen atom, actually just get it out of the system to the background lattice. So that's kind of the main reason that T2 effects are so quick. And another question from last session was actually, why do we talk about hydrogen atoms in water when there's lots of hydrogen in other molecules in the body? This again kind of comes up when we consider T2 effects. So just like T1, T2 varies between tissues, and the presence of lots of other atoms and lots of other hydrogen atoms allows for many variations in the magnetic field, right? So in more fatty tissue where T2 is very quick, that means that the signal that we can record in the transverse plane is gone very fast. I don't know why I snapped there, but it's on the scale of like 10 to 50 milliseconds. It's extremely fast and almost too fast for us to image by conventional means in MRI. So it's more effective to talk about, more useful to talk about water because we can actually image the signal there. Whereas the same principles apply in more fatty tissue and other tissues of the body, but the signal there can be so low that we need to use other strategies to actually investigate or generate contrast in those tissues. And there are ways to do that. That'll come up in a later session. But this is why we usually talk about signal from hydrogen and water. That along with the fact that we have lots of water in our bodies, right? Okay, yeah, I want to get to our graph. Cool, so this comes back to the last graph that I drew last session. The T2 decay graph, or the transverse dephasing graph, right? We start up here with our transverse component at its maximum magnitude, which is kind of like 100% of the NMB in a 90-degree flip is in the transverse plane. So we start up here and then very quickly lose our signal, right? And this this graph is, let me move that out a little bit. Oh no, to draw it again. Will it be better or worse than last time? Hard to say, about the same. Okay, so T2 is our constant when this, this percent of mxy, or the transverse component of our NMB, is at 37% of its maximum. Scroll up, cool. That happens quite quickly, much more quickly than T1 effects do, as we already talked about. But this also is an imaginary curve most of the time, right? Because there are more things that cause variations in the magnetic field across the body, across individual hydrogen atoms, than just this spin-spin interaction that we've been talking about. So in purple, other inhomogeneity factors. I was debating whether to ask the group, but yeah, I will. Just in chat, or you can shout them out if you want. What are some other factors that are going to cause inhomogeneities in the magnetic field in the body? Yeah, Kate says air pockets is like near the sinuses. Absolutely. So I'm going to write that down as, how do I write it down in my notes? Surrounding tissue. Write down different tissues and tissue boundaries. Absolutely. So the actual magnetic conditions of air are very different than CSF or white matter, gray matter, and the boundary between those regions is a really it's an area that's prone to variations in the magnetic field. A couple other ones I'll just kind of slowly jot down, but feel free to, throw other ideas out there. Safia says metal interfaces, absolutely. So I'm going to put in conductive materials because that can generalize to, paramagnetic and diamagnetic materials, which we'll, touch on in fMRI or sooner if anyone would like me to. But yeah, just like the presence of materials like metal or other surfaces in the MRI scanner or in the body that can kind of amplify or weaken the magnetic field, that can cause inhomogeneity. Also, we are going to be talking about magnetic gradients next. So they also can cause dephasing, which is actually quite important. And I'm going to also just say imperfections of the MRI machine. Because even though we have very smart people designing these machines, nothing will ever be precisely perfect, right? So any imperfections of the MRI machine or the B0 field, they're going to cause dephasing just because of variations in the field, magnetic field that's experienced by individual protons. Okay, thanks for that, guys. So the outcome of this is, instead of this great red line of T2 dephasing, we actually see an even more pronounced loss of signal. And this is our T2 star curve, which may have come up in your readings or talks or whatever. It's a very important concept. So instead of T2, we're usually looking at T2 star, which is an even faster dephasing of signal in the transverse plane because of all of these variations in the local magnetic fields that are adding up. Now, there are ways to kind of get around this that I like to talk about a little bit later. So for now, just kind of understand that T2 decay is kind of the natural, irreversible process of dephasing because of spins interacting with each other, whereas T2 star adds on all these extra factors like different tissue types and presence of metal and imperfections in the scanner and things like that to kind of cause even faster dephasing. And that definitely we have to use that information to inform how we image, right? Because if we wait too long, the signal is going to disappear real fast. Okay. Yeah, I want to make sure we get to gradients. So I just want to touch on how the signal that we record, I mentioned it before, it's free induction decay. I'm just going to kind of quickly scroll through this, right? So what a graph, it's fine. It's debating redrawing this, but it's not going to get any better. So this curve, this is the signal that we can record in MRI, essentially. It's called the free induction decay, or FID curve. If you're wondering why I'm not drawing an echo, it's because we're going to talk about that next session. But for now, the signal that we record in MRI, if we just kind of let the transverse component do its thing, it looks something like this, where this curve here of actually like decreasing signal, this would be our T2 star curve, essentially. It's defining, how we lose that amplitude. And the reason that it's, varying up and down in amplitude is because we're measuring from a reference point and the transverse component is precessing, right? So if we just recorded this signal, we would be looking at hydrogen atoms throughout the whole brain or the whole abdomen or wherever it is that you're imaging, right? We haven't done anything to actually get a sense of where our signal is coming from or to spatially encode our signal, which is what we're going to be talking about next. The solution to this is gradients, magnetic gradients. So we'll see the FID curve again. If anyone is kind of wondering about wanting me to dig more into that, totally let me know. But let's talk about gradients for the next little while. Okay, this is a very important concept, so we may touch on it next session as well to make sure everyone has a really good idea of what's going on here. This is our B0 field, right? Now, I'm going to draw 3 atoms, 3 protons. They're just having a great time in the magnetic field, right? They're processing, they're at whatever phase they want because we're just looking at equilibrium. They're all processing at the same rate. My fancy F stands for precession frequency, and it's the gyromagnetic ratio multiplied by the field strength for all of them. Now, if we record signal after we tip these guys, we're going to get that FID curve, and we're going to know, okay, there's 3 hydrogen atoms contributing to our signal. That could be something that we might get just by how large are the amplitude of our free induction decay curve. We can kind of figure that out from the amplitude of our signal, but we don't know, where the signal is actually coming from unless we add gradients to our MRI sequence. The concept of a gradient is a very small magnetic field that I'm drawing large here so you can kind of better understand what's going on. That is actually superimposed upon the B0 field. So I've got two triangles here representing kind of two lobes of magnetic field. So in the middle, we've got like an area where there's no change to the B0 strength, the main magnetic field. And then above that, we have the area where there's kind of a positive magnetic field being added to the B0 field. And then below that, we have our lobe where there's a negative magnetic field that's actually subtracting from the B0 field strength. Now, just a couple of notes here that I want to write down. This field is superimposed over B0. Gradients can add or subtract. To modify field strength, I guess. That's one way of putting it. And I'm going to mark this in a different color. Gradient magnitude is tiny compared to the B0 field. I'll put that in all caps. It's tiny. Now what this means is usually around 1% of the B0 magnitude. So quite small. In terms of actual numbers, gradients, their strength is quantified by kind of like a magnetic field over distance. So at the Children's Hospital, which is where I tend to work, so ACH stands for Alberta Children's Hospital, let's make this a center line. The gradient, maximum gradient strength is about 40 millitesla per meter. Right? So if we're measuring over like a 2-meter space across the body, then we can come up with an 80 millitesla modification to a 3 Tesla field. So that's very, very small compared to the B0 strength. Now we'll kind of move on to talking about what gradients actually do for us. So now we hopefully understand that that we're adding a gradient to change the magnetic field strength that is experienced by different protons. So if we look at this kind of, at this example I've drawn here, the spatial location of these spins now matters. So instead of all their precession frequencies being gamma dot B0, this one at the top here, it's got a positive gradient, right? That's adding on to the B0 field. So now we're just going to say G for gradient strength. Now this precession frequency is increased. It's actually going to be precessing faster because it's experiencing a stronger magnetic field, just because we've added to that magnetic field. Whereas in the middle, there's no change, right? So this is still the right correction, or the correct equation for our middle spin. And then at the bottom here, we've got a negative magnetic field, or negative magnetic gradient that's superimposed onto the B0 field. So this proton is actually going to be precessing slower, right? Does that make sense for everybody? Let me know if not. One area that people can kind of get tripped up with gradients is kind of thinking that we're applying a magnetic field in a different direction than B0. You got to remember with gradients, the magnetic field that we're adding or subtracting, you know, the field that we're superimposing over B0 is always aligned with B0. That's regardless of the direction that the gradient is applied over. So back to Amios, we've got some kind of handy drawings that will help to kind of drive this home if anyone's a little confused what I'm talking about. So here's the gradient I essentially just drew. We've got a body in the bore. We've got the gradient at top there with its positive field and its negative field that's modifying the main magnetic field. And then at the bottom, there's kind of a drawing of arrows that's helping us understand the outcome of this field, right? To the right of the body, near that person's thighs, the field is kind of a smaller arrow, and then that arrow increases in magnitude as you move to the left in this image, right? So At the left side of the MRI bore, there's a stronger magnetic field because that gradient is adding to the B0 field, which is static. It's, in theory, the same everywhere, even though we just talked about how it's never perfect. Now, we also use gradients in other directions, right? So here's one that's applied from the back to the front of the head, kind of from the bottom of the top to the MRI. And we can see a gradient applied in this direction, which I don't really have a cursor here, but you can see the gradient lobe. It's labeled there. It's got the negative yellow portion to it and the positive red portion. And then we can see that in this direction now, if we apply the gradient, it's still modifying the field strength in the B0 direction, right? It's still modifying the main magnetic field. It's not a gradient that has orientation from the back to the front of the head. Sorry, let me rephrase that. The gradient that we're applying here is not a magnetic field with an orientation from the back to the front of the head. It's a variation in magnetic field, but it's still oriented kind of from the bottom to the top of the head in the actual B0 direction. So hopefully that makes sense. And then just in the third direction, briefly, this one might not fit on my screen as well. I'll accept cookies. We've got a gradient here that is applied kind of from the left to the right of this person's head, with the negative lobe in blue on the left and the positive lobe in purple on the right. We can see the outcome in the magnetic field, the B0 field, that the body is experiencing is it's weaker on the left and stronger on the right. So exact same contact, or exact same outcome. No matter which direction we're applying the gradient in, it's always modifying the main magnetic field. So hopefully I've said that enough times for it to stick, but if not, totally fine. I'm sure I'll mention it again in the future. But this is the idea of gradients. These are generated by other coils called gradient coils in the MRI machine. It's not done by our superconductive giant main magnetic field coil. They're separate. And now let's talk about how we use them. The main outcome of gradients is that we're modifying precession frequency, right? And that can have a couple different outcomes. We're actually going to be using gradients to encode spatial location in all three Cartesian or like cardinal, not cardinal, but all three X, Y, and Z directions. And we're going to do that in different ways. So the first of which, and possibly the only one we're going to talk about today, just to make sure you guys aren't here for too long, is slice selection gradient. So I'm going to draw a brain and sagittal view. I'm telling you in case you can't tell, that's what I'm trying to draw. It is a brain and sagittal view, just trust me. I'm going to draw it pretty big starting here. Oh no, that could be better. I'm going to redraw it just because I want it to be a little bit lower. Good enough. A very, very portly brain. All right, so if we're considering the head in an MRI scanner, our BZO field is usually oriented, well, I mean, it's classically oriented from the bottom to the top of the head. So same here. And then I'm going to draw some spins. I'm going to draw 5 of them. I'm just going to draw at equilibrium, although for our purposes, it doesn't really matter. And now, so we've got all these spins. They're in the B0 field. They're going to be processing at the same rate, right? Just going to draw a big F over here. So we fill out my diagram. And we're going to apply a gradient to modify precession frequencies based on location in the Z plane, from the bottom of the top to the head. So let me just draw that out here. Again, I've drawn this gradient, fairly large, just so it's easier for me to draw and easier for you to see. But these are quite small, remember. And now I'm going to separate these into different rows, just quickly. Or different slices, you might say. And you can see where I'm going with that, I'm sure, because we get slices of images from MRI. Okay, so now instead of all of these spins processing at the same frequency, we have, based on the kind of negative to positive gradient that I've drawn, we have our unaffected one in the middle, which I'm just going to say, I'm going to represent its precessional frequency just by like, it's completed one cycle in this amount of time, right? And then as we become more positive, these spins are going to be processing a little bit faster. maybe too fast for my example. So say by the time that this one in the middle finishes one cycle, the one above it is a little bit ahead of it in phase because it's spinning faster. And then same with the one above that, it's processing even faster, right? It's spinning faster. I just want to kind of do away with numbers because they're not really necessary here, although they could be helpful. And then down here, we've got spins that are processing slower. That arrow needs some help. Okay, right? So there's different precessional frequencies based on the spatial location of our protons. Now, what this means is that the B1 field can be applied at frequencies which have an outcome on which slice of tissue gets influenced. So because we need to achieve resonance for spins to actually tip effectively, if we apply the B1 field at the just kind of the standard default precessional frequency that we would expect based on the Larmor equation of gyromagnetic ratio multiplied by B0, we would influence spins in this slice, right? Does that make sense? Kind of getting at how if we apply the B1 field now is at the resonant frequency for our middle slice, but because the protons above and below are spinning faster or slower, our B1 field isn't really affecting them as much. We kind of touched last session on how there's kind of an imperfect resonance response to protons that are spinning close to the same frequency as the B1 field. So there's like going to be some thickness to our slice, and we can kind of account for that to, we can design our B1 field delivery in such a way that we end up getting a slice of an intended thickness of like 1 to 2 millimeters or something like that in MRI. But this also means if we apply a B1 field at a faster frequency, we could tip the NMV in the top slice only, for example. If we had this sine wave with a higher frequency, right? So now we're interacting with the net magnetization vector in different locations, in different slices, just based on the frequency that we're applying it at. I scrolled away a little bit, but just to kind of drive it home a little bit more, if we wanted to get a slice down here, a very thick slice, we would apply a B1 field at a lower frequency, right? And let's just go over to a small animation that might help with this. So in this MBIOS example, we've got our B0 field, we've got our gradient, which they have, only positive, right? From bottom to top, they have weakly positive at the bottom and strongly positive at the top. And then we'll see we've got 3 slices of spins that are processing. And if we apply a B1 field, we can tip only spins in the middle slice. They are doing the 180 degree. Actually, this could be an idea, I guess, based on what I've been talking about today, but it doesn't really matter. The concept here, just to get across, is that the top and bottom slices aren't affected by this B1 pulse because it matches the resonant frequency of the middle slice only. So that's slice selection. If anyone has any questions about that, let me know. But at this point, we've kind of isolated signal in one slice of tissue, so we know that any signal we're getting is from that spatial location. We've spatially encoded the Z direction, and that's 1 of 3, so we're a third of the way there. And then I'll just kind of play this next example as well, which will show you that ultimately this slice has affected protons in the X and Y direction, all X and Y directions, so long as they're at the right Z location, right? So it's not just 3 protons, it's this 3 by 3 matrix of any protons that we're spinning at the right Z location. So we've got a 2D slice now, but we still need to encode our signal in the X and Y directions. Got a question about whether you can apply multiple gradients simultaneously. You can, yes. So this we'll kind of talk about timing of gradients during pulse sequences, which will be most of the focus of next session. There's some logistical concerns when you apply multiple gradients, but generally because we're applying them in X, Y, and Z directions, which are orthogonal, they won't affect each other, and we can still kind of apply the principles of each gradient separately. Generally, when we're doing something like slice selection, we would only have the Z gradient on, not anything in the X and Y direction, because you want to make sure that you're exciting that whole slice. But yeah, when we're talking about like X and Y stuff, which will come up a little bit later, then there's a little bit more, like there's less timing restraints between them. You can apply them simultaneously for sure. In fact, it's quite common to do that. All right, we're going to talk. I will end on frequency encoding, as this is a pretty understandable one. The last one is phase encoding, which we'll start with next session, I suppose, to wrap up gradients and get into pulse sequences, because there's a little bit more, I don't know, maybe a little bit more confusion around phase encoding gradients typically. But now I'm going to draw a axial, or an axial slice of the brain. I'm telling you in case I draw it very poorly. If you thought my sagittal brain was bad, wait till you see my axial one. All right, you start with the ventricles, of course, because otherwise, how do you know where the cortex is? This is my logic. And then you draw a brain like a cloud, because this is definitely the precise shape of a brain and the gyrification you would expect. Great, cloud brain. As everyone knows, the brain is shaped like an arrowhead. Yep, nailed it. Okay, so we have a brain here, and we're going to apply a gradient in the typical X direction, right? So say, I'll just draw a coordinate system here. X direction would be left to right in this brain. We're going to apply a gradient that's negative to positive in the X direction. I'd love this to be more balanced. Now it's just the other way. Fine, fine. Okay, so if we have spins that are, or protons that are in different locations in the X direction, they will, yeah, I think I remember why I did this separately. I lost part of my brain. Just going to draw some bands over here. We're only going to do 3. Not really necessary to do more. I'm going to draw the protons themselves separately, just in a little 3x3 grid over here. All right. So these guys, after excitation, are all processing at the same rate, right? That Larmor frequency, generally, until we apply a gradient. And exact same outcome as in slice selection. Just imagine that this 3x3 grid of protons is overlaid with the brain. It just got a little bit messy when I was trying to combine everything. In these 3 bands, we've got our negative gradient lobe that's going to be affecting this precession frequency, and our positive gradient lobe that's going to be affecting this precession frequency. So the outcome would be that these guys are going to be processing in the middle, kind of unaffected, and if they complete one cycle, the ones to the spatial right of the brain, the actual, like the ones in a different location to the right side of the brain in this diagram, are going to be processing faster, right? And this is, again, very exaggerated just for kind of illustrative purposes only. The actual differences between spins are much less pronounced than this, as you might expect. And then the ones on the left are going to be processing more slowly, right? So the exact same outcome as with the Z direction, we have modification of precession frequencies, but now it's applied in the X direction. And back to our kind of free induction decay curves. Now, if we record signal from this slice, because we've tipped the NMB in only this slice, thanks to our slice selection gradient, and we're changing the frequency of different protons in the X direction, we're going to get a different kind of signal. So I'm going to just quickly label these green, blue, and pink, I guess. Purple. Purple. Although purple was slow before, so I'll keep it slow. All right. So if we just kind of mosey on down a little bit on this page, I haven't left myself too much room. I'm just going to erase this to give myself a bit more room. If we look at actually like the signal that we've measured from our free induction decay curve, which again is kind of like, you know, wiggling up and down and getting smaller and doing all this fun stuff, that kind of curve. Now we would see if we kind of superimpose these, ultimately we're going to be recording one signal, right? Because there's only one transverse component that's processing. It's the sum of all these subcomponents. But if I draw the subcomponents, then if my blue signal, which is in the middle, is doing its classical free induction decay thing, it's processing at a certain frequency, right? And that's what's causing the change from negative to positive. So if we look at the purple signal instead, it's going to actually be processing more slowly, decaying at the same rate, but processing more slowly in general. So that means that this signal might look something like this. Forgive my non-mathematical drawings, but you can see how the curve here, the actual decay rate is similar, but the frequency of precession is slower, right? It's not going up and down as many times as before. Whereas the green signal, that would be actually like a faster precession. Trying to kind of match my previous drawings, but so there'd be a faster frequency of precession, but the curve would be similar. I might want to actually make this one a little bit taller, but so that obviously looks very messy. That's fine. We can break that down later. We don't actually have to worry about these subcomponents in this way. But I wanted to kind of give you the idea that when we're recording signal in the transverse plane, which we do, now we have a signal that's composed of different subfrequencies. In this case, green, blue, and purple. And if we can find a way to separate these frequencies and look at kind of how much signal we get from the purple side of the brain, how much signal we get from the green side of the brain, then now we've encoded signal in the X direction as well. So we've got Z and we've got X, and there's Y left to do. That's through a process called phase encoding instead of frequency encoding. Here, what we've done is modify the frequency and then record that information. We can use that to kind of break down our signal later. So the next one is phase encoding, where we're going to add some phase differences to the signal as well, which is where things get nice and fun, a little bit messy. But we will leave it there for today. Thanks for coming. I see, sorry, one last question I just noticed from recently, so it must be on the slide. Is expecting the red arrows not pointing in the same direction. Yeah, so for this actual, like the timing of this diagram, I've drawn it post excitation, after the slice selection thing has happened and we've tipped the NMB into the transverse plane. And at that point, we would expect our spins to be synchronized. That's why we have a transverse component to our signal, and that's why we can actually record something. So at a different point in time, you could expect the arrows to be pointing in different directions, but at this point, after we've applied the B1 field and now we're recording signal, the spins will be synchronized. And that'll hopefully make a little more sense once we talk about pulse sequences, which is going to be the focus of our third session in 2 weeks. All right, cool. So thanks for coming, everybody. I hope you guys learned something and it wasn't too boring. To that end, though, I've got another just quick feedback form. I'm going to put it in chat here. Please just, if you have any issues or things that work, let me know, just so I can kind of design the next sessions in as effective a way as possible. But otherwise, I will stop recording here and we'll pick up again in 2 weeks. Thanks, everybody.